So this is the second lecture on current mirrors. Last lecture we were looking at this circuit and we had found that this circuit gives a high R out GM4RO 4RO3, but its voltage swing is significantly reduced because the VO min that we can get with this circuit with an VOV of 0.2 volts turns out to be 0.8 volts. From here to here the minimum voltage had to be 0.8 because what we found is that VD1 was 0.6 because of VG1, and then from here to here was another 0.6, so 1.2, and then we had to go down to get 0.6 here. So and then 0.6 plus 0.2 was 0.8, and so the fundamental cause of the high VO min is because of this diode connected M1. So what happens is, as I had said last time, this circuit was used widely as long as the supply voltages were high, 3 volts and all that. But as supply voltages started reducing with technology shrinking, now we get supply voltages of even 1.2 volts. And now if you have a VO min of 0.8 volts, so that the output can swing only from 0.8 to 1.2, that is a very small voltage swing. And so people said, well, this is not good enough, we have to do something. Of course, people said this is not good enough much before we reached 1.2 volts. So the question that was asked was, well, can we modify this circuit so that this M1 is not diode connected, so that we can bring down the drain voltage of M1 to 0.2, the overdrive, and then this will be 0.2 plus 0.6, and this will be minus 0.6, so this can also go down to 0.2. So here is the circuit that achieves this. So instead of connecting the gate of M1 to the drain of M1, the gate of M1 is connected to the drain of M2. Alright. So now this can be, this does not limit the drain voltage of M1 to become 0.6 or VOV plus VT. Now this drain of M1 can be just VOV. Alright. So this is, but let us look at this circuit. So now what has happened is, earlier in the earlier circuit, the gate of M2 was connected to the drain of M2, and so the gate of M2 got a bias by this diode connection. But now we've removed the gate of M2 from being connected to the drain of M2. Obviously we can't connect both the gates to the drain of M2, so now we need to find another bias for the gate of M2 and M4. So here is an additional kind of current mirror kind of thing added. It's actually not a current mirror. It is another circuit that generates a DC voltage, which we had discussed last time. Alright, so this is the circuit. Now how do we design this? So this is how we design. We say that, well, we want this voltage to be a VOV. So let's say 0.2 volts. That means we want this voltage to be 0.2 plus 0.6 or 0.8. And we want this voltage also to be 0.2 volts. Alright. In other words, we want VG2, the gate of M2 and M4, which is being generated by this circuit, to be a VOV1 or VOV3, the same thing, VOV1 plus a VGS of M2. So VOV1 plus VGS of 2, which is 2 VOV1 plus VT, because VGS2 is equal to a VOV1 plus VT. If we do this, then VO min will become 2 VOV, which is 0.4 volts. So with this condition or with this requirement, we can write all the equations. So here are the equations. So we say, well, okay, we want VG2 to be all this, and VG2 of course is equal to VG5 for M5, and the VG for M5 we write VG5 equal to VT plus 2 IRF by mu n C ox W by L 5. So that is just the drain current equation for M5 rewritten for VG5. So that's one equation we have for VG5, and we want VG5 equal to VG2 equal to 2 VOV1 plus VT. also note that VOV1, which is the overdrive of M1, is equal to okay, so this is VG1 minus VT, which is equal to the same thing written for M1. So this we are here we are making the drain currents of both these branches we are keeping the same. So we get 2 IRF, and then this will be W by L1. All right. So we have an expression for VG2 here. We have an expression for VOV1. And so we can equate these two, all right? So we can equate this with this plus Vt. And if we do that, then we get this relationship. So let's go back. How did we get this? See here. So we say Vg5 is Vt plus this, which is Vg2. So Vt plus this is equal to 2VOV1 plus Vt. Vt cancels. So we get this equal to 2VOV1. And VOV1 is this. So we get this equal to twice of this. All right. So that is what this is. This is equal to twice of the W by L1. And if we solve this for W by L5, then we'll get, so you square these and everything cancels except the W by L's. And you'll get W by L5 equal to 1/4 of W by L1. So the 2 becomes 4. All right. And with this, we'll get VOmin equal to 2VOV1. So now we've got a lowest possible VOmin of a cascode circuit. All right. And now one thing to kind of recognize, it's a simple thing, but it's important to remember or understand, is that VG2, this voltage is, we said, like, let's say 0.8 volts. So VG2 is greater than VG1, all right. And this, so if you look at M1 and M5, the gate voltage of M1 is smaller than the gate voltage of M5. Both have the same currents flowing in them. Therefore, because this is larger, the width of M5 will have to be smaller because the same current flows and gate voltage of one is larger than the other, so the width has to be smaller. So that is what this is saying. So if we assume the lengths to be equal, then W5 is smaller than W1. All right. Okay. All right, now we ask the next question. So we have this circuit, low voltage cascode. So by the way, this is called a low voltage cascode. And we have got an R out of GM4, RO4, RO3. Then we ask, well, what if this is not enough? I still want a higher R out. And this does actually happen in circuits, specifically in circuits called current steering digital to analog converters. We in fact look at them just in a few minutes, where this R out is often not enough. All right. So then we say, okay, what can we do to make a current mirror that has even a higher R out? So the obvious thing to do is we say, well, 2 stacked transistors gave us a higher R out. So let us stack 3 transistors. All right. Then it will give an even higher R out. So we had 2. Now we stack 1 more. So this is called a triple cascode. And what is the R out? So the output is here, the load is connected here, and the current in this will be IREF with some biasing which I have not shown. So what is the R out of this? R out of this is GM3RO3 times the resistance looking down from the drain of M2, which will let us call RD2. So the R out is GM3RO3 RD2. And how much is RD2? RD2 is GM2 RO2 RO1. And so we get the R out as GM3 RO3 times GM2 RO2 RO1. So which is of the order of GM squared RO cubed. So alright, so this is a much higher resistance than the double cascode or the normal cascode. Alright, the VOmin one can get, at least theoretically, is 3 VOV, 1 VOV for each of these transistors. But as you can imagine from our discussion of the last few minutes, designing a bias circuit or connecting appropriate mirrors and IRFs and all will not be trivial. So I'm going to leave that as homework. So you complete this mirror. This is not a mirror yet, right? This is just a circuit without a mirror. So make a complete triple cascode mirror with all the mirror transistors and the current sources such that the VO-min of this circuit is 3 VOV. Alright, this is homework for you. Alright, to get an R out of this order, actually there is another circuit that is more popular and it is called a regulated cascode. So let us look at this circuit. So here, so let's look at it two ways. So this is the basic mirror here, M0, M1, IRF, and then M1, M2 is the cascode. Now to the M1 and M2, another transistor M3 is added like this, which is basically the source of M2 is connected to the gate of M3, and from the gate to the drain of M3, M3 is a common source amplifier. So common source amplifier is connected across the source and gate of M2. So let us look at this qualitatively. So let us say that VO increases a little bit delta, and as a result of the VO increasing, this M2, M1 due to channel length modulation, the drain current will tend to increase. Alright, now as the drain current increases, the voltage at this node, which I have called VS2, also increases because of the voltage drop across M1. So if the current in M1 increases, the voltage across it also increases, again due to channel length modulation, because of course we are assuming everything is in saturation. Now as VS2 increases, for the regular cascode, VGS2 decreased and so the current decreased, and therefore the overall change in current was small and so the R out was large. Alright, for the regular cascode. Now what is happening? As VS2 increases, not only is VGS2 decreasing, but because VS2 is increasing, because of M3, the drain voltage of the M2 is decreasing because of this common source amplifier. So VS2 increases, VD3, which is equal to VG2, decreases, and therefore that causes a further decrease in the drain current. So the overall change in the drain current for a small change in VO is extremely small, and the change in the drain current is extremely small, the output resistance will be extremely large. Alright, so I am leaving the as homework for you to prove or find. So draw the small signal circuit and find the Thevenin's resistance looking down from VO of the small signal circuit, and show that that resistance is approximately equal to GM3RO3, GM2RO2, RO1. Alright, so to the GM2RO2, RO1 gets multiplied GM3RO3, the voltage gain of the common source amplifier. So and this is approximate, there will be actually other terms, but those are small compared to this term. This is the dominant term. Also show that the VO-min of this circuit, the lowest voltage that can be achieved while keeping all the transistors in saturation, is VGS3 plus VOV2. Actually there is not much to show, it is obvious from here, but just kind of convince yourselves that VO-min is equal to VOV2 plus VGS3. Alright, now which is equal to all this if the VOVs are equal. So this is true, that 2 VOV plus VT is true only if M2, M3, M1 all have the same VOV, which is not necessarily always the case, because M3 doesn't need to have the same VOV. Alright, now this circuit has the same R out as the triple cascode, the circuit on the previous slide. But it turns out that this circuit is used more widely than the triple cascode, even though the VO-min of this circuit is higher than the triple cascode. But this is a little complex, so we'll come back to this only in chapter 9. Alright, for now we leave this as a current mirror, in chapter 9 we'll build operational amplifiers using these various configurations. Alright, one more last current mirror circuit. So somebody of course asked this question, and perhaps you were also asking yourselves, can I increase R out without increasing Vomin? Right, so the Cascode, the triple Cascode, the regulated Cascode, all increased R out, but their Vomin was increasing, so it was poorer in terms of the voltage swing. So can we increase R out while keeping Vomin equal to VOV of M2? So let's think about how we'll do it, right? So what we want is, we are saying, well, if there is a small increase in VO, and in this circuit, IO will change by an amount equal to VO by the RO of the delta VO divided by the RO of M2. Now we are saying, well, we want IO to change less, alright, so that the RO becomes higher. Now if IO has to change less when VO changes, the only thing we can do in this circuit to make IO change less is somehow make VG1 smaller as VO becomes larger. As VO becomes, VO increases by delta, VG1 should decrease by a delta times a gain. So we say, okay, well, as we did in a regulated Cascode, let's put a common source amplifier from VO to VG1, and then we'll get, as VO increases, VG1 will decrease. But this is a little more tricky, because we have a diode connection here. VG1 is actually fixed by the left hand side circuit. So VG1 can't be changed just by putting a common source amplifier here, because there is another branch. So of course somebody thought, and this is research, this is innovation. So they said, okay, so I already said this. This is a circuit they came up with. This is showing you the paper, the reference from which this circuit came. So instead of a common source amplifier, they put an op-amp between these two nodes and the output at VG1, so that there is no direct connection from the drain to the gate of M1. It's a beautiful innovation. It is very simple, but it achieves a very nice high R out without increasing the the VO min of the current mirror. So here let's qualitatively see what happens. So if VO increases, this is a negative terminal. So VO increases, VG1 decreases, IO decreases, so that the net change in IO is small, and so R out becomes large. All right. To understand actually what is so there are actually two things that determine the VO min here. One is M2, the other is what is happening inside this op-amp. And this we will keep pending until chapter 9, when we'll discuss the design or the internal structures of op-amps. Alright, so that VO min, as far as the op-amp is concerned, we'll keep pending. But let me just tell you that the op-amp will not limit VO min. Let us find R out for this circuit, or maybe I am asking you to find first. So you pause, you solve this the AC circuit and find R out, and then continue. So unlike the regulated Cascode, I am actually solving this. I don't quite remember why I am solving this, but okay, so you solve one, you don't solve one, like that. So okay, so here is a small signal circuit of the low voltage. What is this circuit called? I forgot. Regulated simple mirror, this is called. Alright, so this is a circuit. From the drain of M2 above is an ideal current source, so we open circuit it. We are finding the resistance only looking down from the drain of this transistor, so we are not including the load which is up here. So we connect an external voltage source, we find the current supplied by the voltage source, and then Vx by Ix will give us the R out. So we write the equation. So we start here. The op-amp of course does not draw any current, so this current circulates here, and so we can write for this loop Vd2 is equal to minus GMRO Vg1 which is here. And then for the op amp, we write VG1 is equal to the gain of the op amp A times VD2 minus Vx. This is VD2, this is Vx. So VG1 is A into VD2 minus Vx. VD2 is minus GM RO VG1. And so VG1 we substitute from here. So we'll get A GM RO into Vx minus VD2. So I've changed the sign of this because of this negative sign. And so we solve for VD2 from this. So we get VD2 equal to AGM-RO by 1 plus AGM-RO into Vx. And then, well, of course, we want to find Ix. And Ix is equal to GM VG1 plus Vx by RO. Vx by RO is known. So we need to find GM VG1. We need to find VG1. So VG1 is how much? A into VD2 minus Vx. So we found VD2, so we find VD2 minus Vx as this minus Vx, which turns out to be minus 1 by 1 plus AGM-RO into Vx. And now we having found VD2 minus Vx, we write Ix. So Ix is GM VG1 plus Vx by RO, which is equal to GM into A into VD2 minus Vx plus Vx by RO. And then VD2 minus Vx we substitute from here, which is this plus 1 by RO into Vx. So that is Ix. So then Ix is equal to, so we solve this and we get this. So Vx by Ix is equal to RO into 1 plus GM RO, or RO plus AGM RO squared, which is approximately equal to AGM RO squared, where A is the gain of the op amp. So R-out can be made large by making the gain of the op amp large, or the gain of this circuit large. In fact, if this A is simply 1 in the simplest possible case, even then we get an R-out of GM-RO squared, which is equivalent of a Cascode, with the additional advantage that the VO-min of this circuit is still just 1 VOV. And if A is of the order of GM-RO, we'll get higher. If A is GM squared RO squared, we'll get like a quadruple Cascode. All right. Okay, now let's do a quick design of a simple current mirror circuit as applied to a digital to analog converter. So you are all familiar with digital to analog converters. A DAC is a circuit that converts a digital input to an analog output. What is the relationship between the digital input and the analog output? The mathematical relationship. So I'm asking that question by asking this. So I assume you know. The relationship is that the V out is equal to the digital input converted to a decimal number, which is this, into Vref by 2 raised to n, where Vref is some reference voltage. All right. So whenever a digital number is converted to an analog value, there will be some reference voltage will convert the number to a voltage. That voltage is called as Vref. Alright, so I am assuming you are all familiar with this expression, so I am not discussing it more. Now in this expression, if the input, the digital input, has only the least significant bit 1, and all the other D's, the digital bits, are 0, so then only this term is 1 and all the others are 0, then this will be 1 into Vref by 2 raised to n, and so V out is equal to Vref by 2 raised to n. This is called the resolution of the, this is DAC, it's not an ADC, this is a DAC. This is called the resolution of the DAC. That is, what is a resolution? It is the lowest voltage that can be detected or output by the digital to analog converter. It is also called the LSB, the least significant bit. And in DAC and ADC literature, the LSB is used also for the analog voltage. So this quantity is often called the LSB. Now there are various types of DACs in the world today. The fastest of the DACs are called current steering DACs. In all the video applications, current steering DACs are universally used. So the basic principle of operation of a current steering DAC, and I'm showing a 4-bit current steering DAC, is this. So we'll have current sources coming down from VDD, and there will be switches, and the switches will be controlled by the digital input bits. So if D0 is 0, that switch is connected to ground. If D0 is 1, it is connected to the output node of the DAC. So this is a digital output of the DAC. I'm sorry, the analog output of the DAC. And so if D0 is 1, that I flows through some load resistance and creates a voltage. If D1 is 1, then 2I flows, D2 is 1, 4I flows, D3 is 1, 8I flows. So that the expression for VO can be written as I times RF times the digital input code. And depending on which D's are 1, the actual analog voltage will appear. The LSB, or the resolution of such a DAC, is I times RF, which is the case when only D0 is 1. Alright. Now let us think of a 10-bit current steering DAC. Then we can write the output of that DAC as I times RF times 2 raised to 9 D9 plus 2 raised to 8 D8, etc., etc. So there are 10 bits, D9 to D0. The LSB is IRF. Now let us say, and these are realistic values used in current steering DACs, that the LSB current is 10 microamps. And let us say that the resistance we've put at the output is 200 ohms. Alright, which means that IRF will be 2 millivolts. So the lowest analog voltage after 0 will be 2 millivolts when only the least significant bit is 1. The maximum output will occur when all the bits are 1. So if all the 10 bits are 1, then this number is close to 2 raised to 10, right? It is actually 2 raised to 10 minus 1. And 2 raised to 10 is 1024, so approximately 1000. So then the largest output voltage that will occur when all the bits are 1, and that will be 1000 times 2 millivolts, and that is 2 volts. Alright. Now, because we want the output to be able to change by only 2 millivolts when the least significant bit changes, that means that all the errors, any circuit has errors due to non-idealities, then all the errors put together in the circuit due to all the non-idealities must add up to less than 2 millivolts. And usually the rule of thumb is all the errors must not be more, the sum of all the errors must not be more than half of the LSB, so it should be 1 millivolt. Alright, and that is equivalent to, if you were to think of currents, that comes to 5 microamps with a 200 ohm resistor. Alright, what that means is that, so we have these current sources, and a 10-bit current steering DAC has 10 current sources. Each current source cannot cause an error more than, well, the sum of all the current sources should not, the error in all the current sources should not be more than 5 microamperes. Alright, so with this, let us design a simple current mirror circuit to meet these following specifications. So let's say we want to design a current mirror, this mirror, for the MSB current source, or the most significant bit current source, which is 2 raised to 9 times I, and we are saying I is 5 microamperes, so 2 raised to 9 times I will turn out to be 5.12 milliamperes. And so I'm showing only one of the 10 current sources, and that I'm calling that I0. So the I0 flows through RF, and this is the MSB current source. Now what we are asking is that this current, we need to design this current source by a current mirror circuit such that the error caused by this current source, as VO varies from 0 volts to 2 volts, is less than 2 microamperes. Alright, so what will happen is, you think about it. This VO will change from 0 volts to 2 volts as the digital input changes from all zeros to all ones. Now, and as this changes from 0 to 2 volts, this current mirror circuit, because the voltage across it is changing, its the current will change, right, because of channel length modulation, or in other words, because of the non-infinite output resistance of the current source. As the voltage changes, the current will change, and we are saying the change in the current should be less than 2 microamperes as VO changes from 0 to 2 volts. This is what we need to design, and what we are given is a VDD 3 volts, IREF 10 microamperes. We are told that the length of all our MOSFETs should be 0.5 micrometers, RF is 200 ohms, and we will make a PMOS current mirror because it is coming from VDD to a floating node, so this has to be a PMOS current mirror, and these are the PMOS parameters, our usual ones: minus 0.4 volts, 100 microamp per volt squared, and the lambda is 0.05 per volt. So let us say, okay, now I want a current mirror, so let me start with a, okay, I'm not starting, I'm asking you, so you pause and you see if you can design this current mirror. Okay, it's a very nice exercise to apply all the analysis knowledge to the design of a circuit. So I would strongly recommend you pause for a long time and think and design the circuit, and then only go to the next part of the lecture. Alright, so we say, well, let us start with a simple mirror. Just put M1 and M3 and have an IREF here. So that, and the specifications are that I0 must be 5.12 milliamperes. So our primary concern is how much does VO vary or IO vary as VO varies, alright, and which relates to the R-out of the current mirror circuit. So the R-out of our current mirror is RO3. We know the R-out is RO3, and RO3 is 1 over lambda IO. Lambda is 0.05, IO is 5.12 milliamps, and so our R-out is 3.9 kilo ohms. Now let us see if 3.9 kilo ohms is enough for IO to change by only 2 microamps, for VO changing by 2 volts. So what does this mean? When IO changes by 2 microamps for V changing by 2 volts, that implies an output resistance of delta V by delta I, which is 2 volts by 2 microamps, which is 1 mega ohm. So what we need actually is that the R-out must be at least 1 mega ohm. 9.9 kilo ohm is clearly not large enough. So we say, well, okay, simple mirror is not enough, we need a cascode, and this is a cascode, not a cascade. So we need a cascode current mirror. So we say, okay, let us try a cascode current mirror. So we draw the cascode current mirror and then find its R-out. So we know the expression for the R-out of this is GM4 RO4 RO3, and we can write GM4 RO4 RO3 as 2. So GM4 RO4 is 2 over VOV into lambda, you will hopefully recall, and then RO3 is the same. Why? Because the current is the same, the 5.212 milliamps, the lambda is the same. So this is 3.9 kilo ohms. Now we want a large R-out, and so we say, well, we'll put the smallest possible VOV to get the largest possible R-out. The smallest VOV we know is 0.1 volt, lambda is 0.05. So if we calculate, this turns out to be 1.56 mega ohm, which is good. We wanted greater than 1, we've got 1.56. So we say, okay, a normal cascode is good enough for our design. Then we ask the next question, well, is a regular cascode enough, or do we need a low voltage cascode, which relates to the voltage drop across the two transistors M3, M4. So we know that VO is going to vary from 0 to 2 volts. It will not go above 2 volts for this 10-bit current steering DAC. Therefore, the voltage that we have available to fall across M3, M4 is 1 volt, 3 minus 2. And 1 volt is large enough for the VO of M3, M4. And so we say, well, this regular cascode is enough. We don't need a low voltage cascode. So with this, we find all the numbers. So we have all the numbers, Vt, mu, Pcox, lambda is there, Iref is there, I naught is there, VOV we've decided to be 0.1 volt. So we are taking this to be Iref. Actually, this Iref is not necessary that it is 10 microamps, but I am taking it as 10 microamps because there is no need to put a larger current here because it is simply consume more power. So usually in a current steering DAC, the Iref of the current mirror the originating circuit is kept as the LSB current, which is 10 microamperes. All right, so we know everything in the current expression except the W's. So we write the expression for W. So W1 and 2, which have 10 microamp, we write as 2 RFL mu Pcox VOV squared. We know everything, so it turns out to be 10 micrometers. W3, 4, which are carrying 5.12 milliamperes, will be very large in size. In fact, the ratio of 10 micro to 5.12 milli, right? So 5120 times 10 micro, which is 5.12 millimeters. This is a very wide transistor, but this is okay. Current steering DACs do require very large sized transistors. Alright, so that completes our design. Now I'm leaving you with a question and I'm not answering. I want you to think about it. So as I have said every time, once we design a circuit, we must analyze it and make sure that the design is correct. So the question is, how will we verify that our design is correct? In this case, previous designs were amplifiers and we verified by finding the amplifier gain and the amplifier output resistance. Here what we want to verify is that this circuit with these W's, all right, and the RF of 10 microamps will give an output of, what will it do? Will be such that as VO changes from 0 volts to 2 volts, the current will change only by 2 microamperes. Alright, so how do we verify this? So you please think about it. Okay, so that ends this lecture and the chapter on current mirrors. Next lecture we'll go to differential amplifiers. Actually in Razavi the differential amplifier chapter is before the current mirror chapter, but I have reversed the order. Alright.